Okay, hey, this is Stereo Police. I'm back with my final, or what I hope to be my final video on the great DAC off of 2017. And as you can see, I still have all three DACs. I still have the DAC3 Benchmark, Schiit, Bifrost Multi-Bit, and TEAC NT-503. And it's been probably a month since I made my last video. I didn't intend for that to be the case. I wanted to make that final video ASAP. However, things happened and I had to go out of town and got busy at work. Had to do some projects around the house, and one thing led to another, and I just didn't have the time to devote to making the kind of video I wanted to make for the final. And of course, the final, my final selection is down to between the Schiit and the TEAC. And I will say about all three of these DACs, they're all fantastic. There's nothing really wrong with any of them, but I'm doing an A to B comparison, and this time I did some long-term listening to the DACs to figure out which one I wanted to keep. However, because I got busy and well, long story short, it looks like I'm going to be keeping all three because I've exceeded the return period for the TEAC and the DAC3, and there's no real way to return them now. So that's a bit of a dilemma. I didn't expect to spend that much money, but but nevertheless, I still want to find the best DAC for listening. When I get down to the point where I can sit down here and do some casual or some serious listening and some just enjoyment of music, I want the best of these three DACs, the one that sounds best to me, and that's the one that's going to be permanently in my system. I don't know what I'm going to do with the other two, although the TEAC is nice because it has a Bluetooth link, and I'm able to stream YouTube videos. I sit out back right here and go outside, see what kind of day it is. Haven't been outside yet. Oftentimes I sit out back right here with some friends, and they prefer to just look up songs on YouTube and play those. Not that it's particularly high fidelity, but it's convenient to link the phone to the TEAC and with a Bluetooth link and play videos, songs. So that has that feature. The Schiit doesn't have Bluetooth. Yeah, so I got busy doing so many things, and one of the things I did is built these louvers right here because the sun directly hits us during the course of the day out back there, and it made it impossible to even sit out here, especially in the evening. So I built those louvers. Oh, geez, so many other projects. I had to go out of town. So anyway, that's why it's been a month. It is a nice day. It's fall time here in Virginia. Leaves are changing. I don't know if you can see the mountains over there. Yeah, you can't see it from here. You can see it from the front yard. Anyway, so before I get down to the winner, and I have a winner, one that the DAC that it's going to be permanently in my system. Before I do that, I want to cover some of the technical differences between these DACs. I find it interesting, and for example, the Schiit Bifrost Multi-Bit. With the Bifrost, there's two options basically. Well, they have options for power and some other things, but the two main options for this is the regular Bifrost and the Bifrost Multi-Bit. And what does multi-bit mean? Well, it has a distinct meaning with respect to the type of analog the type of digital to analog converter chip that's being used. And this is a multi-bit R2R ladder type DAC, whereas the DAC3 as well as the TEAC both use delta sigma type DACs, and those are single bit DACs. So multi-bit, single bit. And there's a distinct difference in terms of how they operate. And I would say this, that the R2R ladder multi-bit DACs are, to kind of use an analogy, that's a really bad analogy, I don't know how to really state it, but it's old school technology. It's the way things were done in the 80s, basically, even before that. It's an R2R ladder type DAC is relatively easy, simple. It's a simple process, and it's a very direct way of converting a digital signal to an analog. Although it was hard to make, it requires precision resistors, and that technology has been refined using laser etching and various things to where the R2R ladder DACs are way better today than they were. The chips are. Whereas delta sigma style of DACs, even though I forget the guy's name who wrote the original paper on it, even though it's an old technology, it goes way back, the implementation of this style DAC is more of a recent thing, because it requires super high speed chips, and and so it's kind of become the standard delta sigma in the industry, but the DACs that seem to measure the best in performance are the delta sigma styles. But to use an analogy, I would say that, oh gosh, I shouldn't use an analogy, but this would be more like a tube amplifier versus a transistor amplifier in terms of this being old technology, a fundamentally different way of converting digital to analog, a more direct way. This is a very indirect way of converting digital to analog, and a lot more complicated. A hell of a lot more complicated. This style DAC has to utterly destroy the signal and then rebuild it, so to speak. Whereas this is a very direct conversion. So I liken this to like a triode tube, versus a complicated transistor feedback amplifier in terms of the way they convert. Now, does it result in a difference in the sound? I don't know. I do know that the delta sigmas produce a lot less noise, way below the threshold of hearing, although both are capable of producing analog signals with low distortion. That's not a problem. I often wonder why DACs sound so different from one another, and I don't know that it's the style of digital to analog converter chip it's using, or whether it's the analog circuitry itself, the analog output stages. I just don't know, but they all, when you sit down and do an A/B, they do have their distinct characteristics. They're not the same, when you really sit down and listen. So just a couple of notes I want to cover between, and this, if you're not interested in this stuff, if you want to get right to the finals as to which one won, you can probably skip this video. I'm probably going to do that in the next video. I just want to cover the differences, the technical differences between the TEAC and the Schiit. For that, I think I'm going to pop this camera on the tripod. We'll see if I can do this without a cut. I've gotten so busy doing things that the projects I have sitting on my bench here have gone untouched, but I guess that's a good thing. It's always good to have things to do. Okay. I just cut and pasted some miscellaneous things from the web onto a PowerPoint just to have some things to talk about, technical wise. And again, technical stuff, fast forward through this if you don't want to hear it, but I find this stuff interesting and probably a few people might. Let's talk about the Schiit Bifrost multi-bit. And again, I just have these notes for me to remind myself what I want to talk about here. So the Schiit, again, comes in two options. The Bifrost multi-bit comes with is supplied with an Analog Devices AD5547 Cruise DAC. Interestingly, this particular DAC wasn't intended for, it wasn't designed for music signals. I'm trying to find the right glasses. I'm in that range where I can't see. Okay. From the Analog Devices datasheet, the DAC is designed for automotive or automatic test equipment, instrumentation, digitally controlled calibration, digital waveform generators. It is a precision DAC, but nowhere does it mention music. It is also a 16-bit DAC, meaning it can accept or receive a 16-bit signal, a 16-bit digital value and convert it to an analog value. And 16-bit is one of the standards. It's the standard for compact disc and others. Standard for many streaming services, Sonos, and many others. So it's a 16-bit DAC. The general description is a let me have to lift this for a second. This DAC is a dual precision 16/14-bit multiplying low power current output parallel input DAC, designed to operate from a single 5-volt supply with plus or minus 10-volt references. Okay, so you can see from the diagrams on the data sheet that it is an R2R ladder style DAC. I'll cover it more. And there's our our diagram. Here's the DAC itself. It's a 16-bit DAC, and the analog signal has to be pushed into some sort of a analog gain stage for the output. I don't know what Schiit is using here. Are they using an op amp or discrete components? It doesn't say on their website. For the non-multi-bit, it says it has discrete JFET stages, but it doesn't say for the multi-bit. I suspect they're using an op amp of some kind, a low noise op amp. I don't know. I do know that the one of the prices I got online for this particular DAC for the Analog Devices 5547, 25 bucks each. It's pretty expensive for a semiconductor chip. Now, I want to talk about very briefly what multi-bit means versus single bit for the Delta Sigma style. Before I get into that, just a general discussion of PCM. This is basically what comes out of a CD and what comes from most streaming services. Pulse code modulation. To create a PCM signal, first an analog signal is sampled at a certain sampling rate, such as 44.1 kilohertz for the Red Book CD. It's higher for DVD, 48 kilohertz for DVD. So various sample points in time are selected, and then each point in amplitude at that point in time is quantized into a value, a digital value. And that quantized digital value is 16 bits of resolution. And that 16 bits has to represent that particular point voltage level in time. So what you end up getting out here is a stream of numbers. Each number, it's more complicated than this in real life, it's just a simplistic way, but each number represents one sample point in time. It represents the amplitude of one sample point in time. So it's a stream of numbers. Each is 16 bits. For different digital standards, for high res, it's higher than that, obviously, and the sampling rate is higher as well. But we're going to stick with what I'm currently using that comes out of the Sonos digital outputs, PCM 16-bit 44.1 kilohertz. Now, an R2R ladder style DAC, digital to analog converter, kind of looks like this, and I'm not going to get into tremendous amount of detail, but each bit, and this is an 8-bit right here, okay, D0 through D7. So you would, double the length of that for 16 bits, but assuming we have an 8-bit signal, and each bit in the signal, so, each bit in the signal controls one of these switches right here. For example, if we have an 8-bit signal of 0, 0, 0, 1, let's say, could be anything, then all of these switches would be open here, except that one that's a 1 would be closed. And the one that's closed feeds the reference voltage to the op amp. The more of these that are 1s, the more of these switches that are closed, the higher that voltage is going to be. So what we end up getting out is every time a digital a value is fed into here, we get a discrete plateau of a voltage right here. So in this case, the signal is, every time we get an input, we get one voltage level. Then a new signal comes in, then we get to another one. In this case, we have a rising signal. Then a new word comes in, let's say we get another signal. And you end up with this stair-stepped analog output. And this is an analog output. It's not digital. Although it's horribly distorted because it has a lot of high frequency noise. Anytime you have an edge in a signal, that's all super high frequencies. So what we need to do to get rid of that stuff is we pass it through a low pass filter. Analog low pass filter. And it smooths that out, and you're left with the fundamental, which is a smoothly varying signal. And if you want to run some numbers, interestingly, I actually calculated these numbers over here, and I'll just let you, if you want to pause the video and run them yourself, but I have this little sample R2R DAC right here with the voltage out is equal to the reference voltage, which is Vref right here, that's fed into the switches, and followed by this equation, 1 plus RF, that's the feedback resistor there, followed by the R's. Okay, this is an R2R ladder. Every resistor is either an R or a 2R. So if this was 1K, that would be 2K, for example. Okay, so the rest of the calculations, each of these right here, BN, is the highest one, the highest B3 right in that case. And then this last one, B1, is going to be the lowest one over here, which is equivalent to B0. Okay, so this is the most significant bit, and this is the least significant bit right there. So just running some numbers, if I had a binary input right here, this is 4 bits right here. You can see it's we have a 4-bit DAC, but it's the same regardless. If I had input 0000, okay, and if I assumed a V reference of 1 volt and an RF feedback resistor equal to R, any of these resistors, V out would be equal to 0. Okay, I just put them all in there. 0, 0, 0, so that's all 0, right? 1 plus RF, or it doesn't matter because this whole thing is 0. That 0 multiplied by either one of these is going to be 0. So 0 out, right? If I had nothing but 1s on the input, then basically you put the 1s in there. 1s on the input would actually close all of these switches, okay? And with these switches closed, the 1s and the 0s control the opening and closing of the switches, right? So if 1s were in here, the switches would be closed, and every single one of these BNs would be equal to Vref. So they would all equal 1. And here's the numbers being crunched right here. And then the output would be 1.875. And then I did some in-between value where the binary input was 1000. So that's pretty easy because, we have Vref as 1. 1 plus 1 over 1 is going to be 2. And then the only one, Bn, is the most significant bit. So that's all these others are going to be zeroed out. That would be, Bn would be 1 divided by 2, 1/2. So the output would be 1 times 2 times 0.5 is 1 volt. So you can see we have 0 volts out, 1 volt, and then we have our highest possible voltage with all ones right there, 1.875. So you'd swing between 0 and almost 2 volts. So I know it's kind of boring, but you could sit there and try this exercise for yourself. It's a very simple way, and you end up, so when you start getting different numbers in that follows an analog signal, like I said, you end up getting out a bunch of stair steps like this. That is an analog of the original signal, and then once you filter them, you get the original signal back. So this is an R2R ladder. It's a very direct way. Okay, input number, boom, you get an output voltage. Another input number, boom, you get an output voltage. Very direct, very simple way of converting a digital word to an analog output. Now, and this is what the Schiit Bifrost multi-bit uses. Again, right from the data sheet of the analog devices, AD5547, a very straightforward, simple R2R ladder. Piece of cake. Now, old school technology, but it works great. Produces a lot more noise than a Delta Sigma, but these are currently this analog device's DAC is a precision DAC, and its ability with respect to distortion, it should be equal with respect to its ability to convert digital to analog signals. It should be equal to the Delta Sigma. Noise, it's the noise that the Delta Sigma has the advantage. Now, the TEAC, on the other hand, uses a Verita AK4490, and that is designed and manufactured by AK Micro Devices, a Japanese company. One thing I'll say before I get into the Delta Sigma is that on their website, TEAC focuses on and boasts about their analog circuitry. They use discrete. They claim to use discrete, purpose-designed analog buffers on the output. They make a big fuss about it on their website. I won't read all this to you. Carefully designed, discrete, all this stuff. So this could be a clue because they spent so much time on their analog section. Ultimately, you go from the DAC, from the digital to analog conversion, and you do your filtering, but you still have to have an analog buffer on the output. Some kind of an analog amplifier or buffer. And regardless of how good the DAC chip is, if your amplifier buffer is horrible, then that's going to be the weak link in the chain. And TEAC really describes pretty well what they're doing here, and they seem to have cared quite a bit about it. So this could explain perhaps the reason why, and by the way, the analog output sections could also explain why DACs sound different from one another. That's my theory, at least. It could be the analog section. But the fact that it's such a carefully designed analog section could explain why I liked it so much. Just not sure, though. Now, here is the AK Micro Devices internal diagram of their DAC. The AK4490, and it is a, you can't see that or not, it's a delta sigma modulator. The heart, this is the heart of the conversion method. It's not an R2R ladder, it's a delta sigma. And so we're, and it also has a bypass. So if you're receiving DSD data, this has the ability to completely bypass the delta sigma, because DSD data is already delta sigma modulated. So you don't need to do it again. But if you're receiving PCM, then the PCM must be, the interpolator right here is for upsampling. And the TEAC has the ability to upsample PCM data before it delta sigma modulates. But regardless of whether it's upsampled, the PCM data comes into the delta sigma, and the delta sigma modulator produces a delta sigma modulated signal, which looks absolutely nothing like the output of an R2R ladder. In fact, what comes out of the delta sigma, if you were to look at it on an oscilloscope, is almost unrecognizable. You looked at the output of that R2R. Where is that? You look at the output of the R2R, and it's a stepped output, but it looks like a sine wave, or it looks like a music signal. What comes out of the delta sigma is just a bunch of pulses that you wouldn't be able to tell what the hell it is. This is a representation, but it's not a very good representation of what comes out of it. But so the way a delta sigma works, and I'll try to avoid getting into too much detail, but essentially your PCM comes in, okay, and this PCM is drawn in the form of a stair-step thing, but really it's just each of these is just a digital a digital number. That's 4-bit. So what comes in is a series of digital numbers, XXX, right? So we get a first digital number right here, and then it stops. It's parked right there, right? And then the delta sigma takes that number through a series of iterations, okay, in a feedback loop. And during those series of iterations, it pumps out a bunch of pulses, a whole bunch of pulses. One pulse for each iteration, let's say, either a negative or a positive, right? And then that series or collection of pulses represents that one number that's been sitting there. And then it repeats it. It repeats it over and over again. So we get, let's say we get, on the input we get number in, we get a series of pulses out. X, 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 Y, a new number in, another series of pulses out. Each of these series of pulses, the density of those pulses, the proportion of the highs to the lows represents the voltage that's represented by that number. So for example, if this number right here on a 4-bit DAC was 1111, you would see a series, you would see almost all ones during that, during that time frame. If this one here represented 0000 in the next time frame, during that time frame, you would see the density of the pulses would be, almost none. So if you were to average out the pulses within that period, that average voltage would represent the voltage or level or amplitude represented by that digital number. Now, so this is kind of a representation. It's not a very good one. This is not very realistic, but you can see that you have a sine wave, and as the voltage increases, the density of positives increase, and then as the sine wave decreases, the density of positives decrease, and you end up with no voltage here. And if you were to take this type of signal, even though it looks different from the R2R, nevertheless, if you were to take averages every now and then, you know, here and then there and then there, the averages within those pulses would equal to a sample point of voltage up here. Okay, and you can see the average over of this span right here is the highest it's going to get, so to speak. So that's once you pass this delta sigma modulator output through a low pass filter, it achieves the same effect as the R2R ladder. You'll get the sine wave. Now it's not quite that simple, but that's a good enough explanation for now. Oh, and why do they call it a 1-bit DAC? Okay, so this is a bad diagram. A better diagram. Let me see. What if I had one? Yeah, a better diagram is of a delta sigma modulator is right here. And again, without getting into the details, and we could run some numbers in a simulated one here, and it would make sense, but no time for that today. Is the digital number x in the case of 4-bit that would rest right here starts out with in a difference amplifier, and difference, the word the symbol delta is used in engineering and science to mean difference. Sigma is used in engineering and science to usually mean summation, and that's what an integrator does. So your digital value, and this is done in digital circuitry in these two steps right here. In an analog to digital converter, these are done using analog circuits right here. But in digital, these are digital circuits. So you have a digital summer here that sums the output of a 1-bit DAC right here in a feedback loop. So it takes the difference between that and this right here, and whatever the difference is summed up right here. So this continues to sum the inputs and either rises or falls, okay, depending on what the input is. And then it goes into a comparator that produces, this comparator is basically an analog to digital converter, or a digital to analog converter in this case, but it produces an output that's usually either a 1 or a 0, something along those lines. That's fed back to the DAC, which compares that output to a reference voltage, and then what comes out of here is going to be an analog level. That's going to be either ground or the reference voltage. And so what happens is, this happens over and over again. This thing goes into a hunting expedition, and it continues to hunt to find that value. So this thing is going to turn on right here, and then that's too much, and the next cycle it's going to turn off, and then it gets to a point where it's got to turn on and turn off, and it produces that series of pulses. Now, I realize that's overly simplistic, but there's more information available online. I think I might make a detailed video about how these delta sigmas work with running some real numbers. It's kind of fascinating, but this continues to hunt in a series of cycles, and when it's all done, when the number of cycles necessary is done to represent that input number, again, you end up with the density of the ones versus the zeros during that period of time. The density of the ones versus the zeros is equivalent to that number right there. And that's what you have. So it's got a 1-bit DAC built into it. That 1-bit DAC is either on or off. But it's able to produce an output equivalent to the 4 bits because it goes in that 1-bit DAC operates in a series of cycles over and over again to produce that series of pulses, the density of which, the ratio of the highs versus the lows is equal to that input number. But it does it in a one bit series of operations versus our R2R ladder that does it all at once. Boom, you put a number in, pop, you get a number out. Put a new number in, get another number out. Does it in parallel, so to speak, simultaneously, whereas the delta sigma has to go through a number of cycles because it has a 1-bit DAC, and it's got to go through the cycles to produce a series of waveforms that represent that number. Okay, I know I've said it, just thinking out loud here. So that's a delta sigma. Interestingly, the Verita DAC that the TEAC uses And by the way, as well as the Schiit Bifrost non-multi-bit, it uses this same DAC. Price on that, $5 if you were to buy the chip. So I don't know if that's any indicator of anything, but the Analog Devices chip is a hell of a lot more expensive than the Delta Sigma Verita chip used in the TEAC. So there we have it. I realize that I have, this is not a very sort of professional overview explanation. It's kind of off the cuff. I just threw all this stuff together, and I'm sort of talking about it off the top of my head here. But the point is, there are differences, fundamental differences in the way the Schiit operates versus the TEAC and the benchmark. And I know that those of us who are audiophiles, a lot of us really like looking into that and thinking about that stuff and trying to figure out how things work, or maybe why, account for why they might sound different. And sometimes it's just nostalgic, when I listen to my tube amplifier, it's just kind of cool. I like watching the tubes glow and knowing that transistors are literally flying through space inside of a vacuum tube from a plate to a grid, through a grid, and I should say from a heated cathode through a grid to a plate, literally flying through space. It's just kind of cool. I like that. And maybe psychologically that has an impact on how I think it sounds. Although I do know that tube amps sound fundamentally different from transistor amps from experience. Excuse me. So, to me, it's kind of neat. It's kind of neat to know that the Schiit uses an R2R ladder. It's kind of an old school technology, and it's kind of really cool that they went out and they chose this 16-bit chip that has nothing to do with audio, but yet it works. They used it to decode PCM, and I just think that's kind of neat that they're using an R2R, kind of old school. I don't think hardly anyone's using those anymore. And it sounds great. So I think what I'll do is go ahead and wrap this up and get back to the finals of who won. I think you'll find that interesting. I also spent a lot of time listening to the Schiit and the TEAC. Unlike my previous videos, I've had about a month now. Used them both for background music and just doing a lot of listening to them. So I've gotten to know their characteristics much more intimately than I did in all the other reviews. And there was one that I kept kind of wanting to listen to. I'd have the other one playing, and then there was always like, well, I kind of want to hear the other one. The winner, let's say. One of them just had a much better sound, although the one that won and has the better sound does have something about it that I don't like. So, as much. So I will get into that in the next video. Just wanted to stop and take a break and discuss the technical aspects here. So look forward to the next video coming in a day or so. And that will be the finals, the winner, and then a brief summary of the whole thing. Ciao.